All right, let's go. All right, so the first condition for time travel that needs to be satisfied is the time needs to be a continuum. And according to Einstein's theory of gravity, it is, so which means, according to the theory of the future, the present, the past, all happen at the same time. So the question is Einstein's theory proven to be correct? Is this a scientific fact, or is this just that theory? All right, so that's the only one that we will get to explore. Einstein's theory of gravity is the last and the greatest theory in classical physics. And it took him 10 years to develop this theory. So I'm just going to step you through the logic behind it as well as the history behind it. So what's gravity? According to Newton, gravity is just a force. According to Einstein, it's a lot more than that. All right, so special theory of relativity is related. It's a special case of motion near the light speed in a straight line. So you weren't speeding up or slowing down or changing direction, so there was no acceleration involved. Einstein wanted to come up with a generalized theory of relativity, including acceleration. This was meant to be a theory of gravity.
And long before Einstein, the quest for unification began with the most famous accident in the history of science.
As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe.
In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity.
The unification of the celestial with the terrestrial, that the same laws that govern the planets in their motions govern the tides and the falling of fruit here on Earth. It was a fantastic unification of our picture of nature.
Gravity was the first force to be understood scientifically, though 3 more would eventually follow. And although Newton discovered his law of gravity more than 300 years ago, his equations describing this force make such accurate predictions that we still make use of them today.
In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon. Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works.
No kidding. What's gravity according to Newton? It's just a force. The effect of that force is acceleration, which could be described in terms of this equation. Acceleration due to gravity depends on the mass of the planet, and it's inversely related to the size of the planet, the square of the size of the planet. That's it. How does gravity work? How does the force of gravity extend all the way out to the moon and beyond without the Earth touching the moon? For you to be able to accelerate something, you have to apply a force on it. And the object is going to accelerate in the direction of the force, pull or the push. If I'm not touching it, this thing is not going to accelerate this way or that way. So how do you transmit the force? Through the empty space, a distance of 250,000 miles, the force of gravity, all the way out to the moon without any physical contact between the Earth and the moon. When asked this question, Newton said, I have no idea. I have no hypothesis. He didn't even have a theory. He said, the only thing I know is this theory is correct because it makes predictions, numeric predictions, and those predictions match the experimental results. He said, I'm going to leave it up to the next generations, the future generations of physicists to figure this out. Eventually, the future generations came up with the force field idea. So the question is, gravitational force field, how long would it take for it to extend all the way out to the moon and beyond? As far as Newtonian physics is concerned, this would happen instantly. So gravity is an instantaneous force. It wouldn't take no time at all for gravity to extend all the way out to the moon and beyond. Immediately, Einstein had a problem with it. As far as Einstein is concerned, nothing in the universe should travel at the light speed or faster. Nothing in the universe should travel faster than light. The only thing, as far as he was concerned, that could travel at the light speed was light itself.
For nearly 250 years, scientists were content to look the other way when confronted with this mystery. But in the early 1900s, an unknown clerk working in the Swiss patent office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery: that the velocity of light is a kind of cosmic speed limit, a speed that nothing in the universe can exceed. But no sooner had the young Einstein published this idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with,
Let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears.
now let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space.
In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory.
A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss patent office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
If Newton is wrong, then why do the planets stay up? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits that they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now
If the sun disappears, the gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It's warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
So here's a question for you. Now that we know the solution, how do you come up with the theory in the first place? How do you solve a problem like this? Where do you begin?
Albert Einstein, among other things, revolutionized the way we think about good old gravity.
Astronomers generally only talk about one force, and that's gravity. And the reason for it is almost everything that's important on the large scale, that's on the scale of planets and stars or the universe as a whole, is gravity.
From Einstein, we know that the gravity that pulled Newton's apple down from the tree isn't a kind of magnetism. Gravity is a property of matter and space. Matter bends space. The more mass, the more space around the mass is warped. That's why the moon goes around the Earth. It's trapped in a dimple in space, a gravity pit created by the mass of the Earth. When enough matter collects, gravity...
All All right, pick out the best answer.
A.
A.
All right, so A is the best answer. So those of you guys who said A, 5 points. Those of you guys who pick A, give yourselves 2. How do you come up with a theory like this? How do you even start a problem like this?
Gravity is the most democratic phenomenon in the universe. It treats every object the same, no matter what it is made of, no matter how big it is. There were no exceptions to give Einstein a place to start. He had no idea how to approach the problem until...
Then all of a sudden, it occurred to me. Der glücklichste Gedanke meines Lebens, the happiest thought of my life. If a man falls from the roof of a house, he will not feel his own weight.
In another of his thought experiments, Einstein...
All right, so you're in a falling elevator. In a free fall, what does that feel like? If gravity is the only force acting, what does that feel like? Nothing. You will feel weightless, guys. You and the elevator are falling at the same rate. You're standing on the floor. You and the elevator are falling at the same rate. You will appear weightless. You're not going to be able to feel the floor under your feet. You will feel weightless. That's what it means.
Put the idea this way.
Check your center mass.
As he and the elevator both free fall at the same rate in the Earth's gravitational field.
You will also feel weightless in space, especially in deep space.
Then Einstein changed the scene. What if the passenger were in a rocket ship far from Earth? He would still float with no gravitational field to hold his feet to the floor.
What would happen if the elevator were to accelerate in the upward direction, guys? What is that? What do you suppose that would feel like? If you're yeah, go ahead. Yeah, if you're standing on a number one, you will feel heavier. If you're standing on a scale, you will appear heavier according to the scale because of your inertia. Your body is going to resist change in motion. All right, your body has a tendency to retain change in motion, so your body is going to try to resist change in motion. If the acceleration is the same, has a value which is identical to the gravitational acceleration, then it's going to feel like gravity.
On its way up, it would catch the passenger, and to him, it would seem that gravity was holding his feet to the floor.
So if you're in a rocket ship, that's...
This equivalence of acceleration and gravity interesting. But only he realized that it could serve as the foundation of what would become a revolutionary new theory of gravity.
To be honest with you, no one cared. All right, the next step, interesting. So now he's coming up with a new theory. He's trying to come up with a theory of gravity. And so this is another relativity. This time it's including acceleration. So once again, he's got 2 postulates. Postulate number 1 is the same as his previous postulate. So you're inside a reference frame. All right, all laws of physics will be the same in this reference frame, whether it's an inertial or accelerating reference frame, as far as he's concerned. The other thing that he figures out is the accelerating in space at a rate that equals to the gravitational acceleration is going to be the same as. It's going to be felt like gravity. That's it. All right, so the next step is the one that is going to actually nail the theory. We're going to get back to light again, so we have enough of a conceptual background in this. Imagine a light ray in space. It's going to move at the light speed, right? In a straight line at a constant speed. What if you're accelerating with respect to it? What if you're accelerating relative to light? What does that look like? If you're speeding up relative to light in your reference frame, the light is going to look bent.
The other side at a lower point than it entered.
Oh, so here's the catch. If you're in an accelerating reference frame, light is going to look bent in that reference frame. If there's no difference between gravity and accelerating in space, while you're accelerating in space, if light looks bent, the gravity should do the same, which means that the gravity is also going to bend light.
To a passenger, the light appears to curve. If acceleration can bend light, then by the equivalence principle,
gravity should do the same.
Gravity must do the same. It seemed a
So, which means that gravity is going to affect the direction of light. That's what it means.
crucial clue. But where would it lead?